I would like to introduce our next student speakers, Samyak Sarnayak and Ritik Hariani from PES University. They are presenting their paper entitled Architecting and Deploying Optimized GANs with Minimal Footprint for Fashion Synthesis. To the presenters, you have 20 minutes to conclude your presentation, and the last 10 minutes will be used for a Q&A session. You can now share your screen, and good luck.
Thank you, Anaga, for the introduction. I'll share my screen right away. Anaga, is my screen visible?
Yeah, it's visible.
All right. Yep, I think we'll start right now. Yep. Good afternoon, everyone. Thank you for joining us today. Today, myself, Ritik Hariani, and Samyak are going to present our paper, Architecting and Deploying Optimized GANs with Minimal Footprint, who we worked under the guidance of Professor K.S. Srinivas from PS University. Coming to the problem statement. So basic average fashion designer struggles with 3 problems during their career. Is basically for high production time when they're trying to come up with a clothing line and try to produce it with the manufacturer. Coming up with high ideation time, they usually take around a few months to few weeks to come up with clothing ideas. And also during this time, since it takes a lot of time of these factors, they result in producing a low output volume of clothing. So how do these big MNCs companies tackle this problem? Based on our research, we found out that they use a technique called as generative adversarial network. Since the large MNCs have high computing power and they have access to a lot of computer resources, and not an every average designer would have knowledge in the field of artificial intelligence and all that. We plan to provide a client-based solution where average designer can run it himself on his own browser or a mobile phone. Coming to how we plan to achieve this is using, since we all know that generative adversarial networks are very high-weighted CNN networks, we plan to reduce and prune them by using optimization techniques such as lottery ticket hypothesis and also early bird techniques, where we can successfully reduce the size by 16 times. And by pruning it to around 55%, we can also improve the training speed and also the inference time by around 21 times. So coming to GANs, what are GANs basically? GANs was introduced by Ian Goodfellow in the year 2014. So generative adversarial networks consist of 2 models, a generator and a discriminator. What a generator basically does is to capture the data distribution of the data set, whereas a discriminator tries to determine the probability that this data point belongs to so-and-so data set. So these two are basically CNN networks, which are trained simultaneously in the Minimax 2-player zero-sum game. And when they both reach Nash equilibrium, they are said to have converged. So since because they are CNN networks, they obviously would involve a lot of back propagation. Since our use case is to be with images, and since we deal with a lot of images, we plan to use deep convolution GANs, where the architecture of the CNN involves a convolution layers with a Bash normalization. And for the generator, we use activation layer of a ReLU, while the discriminator, we use a leaky ReLU activation layer. To provide the average designer with control over the noise vectors, where he can choose to add his own styles to the images and different colors, etc. We provide him labels where we can incorporate it using conditional generative adversarial networks, which gives him control over the outputs and the certain type of clothes he wants to generate for himself. I would like to transfer the mic to Samyak so that he could explain it in more detail to you. Thank you.
Thank you, Ritik. Pruning techniques are used in neural networks to reduce computation and memory usage. And this is done by removing certain weights of the network. So in this lottery ticket hypothesis, the weights which have high magnitude are kept, and the ones which are closer to zero will not contribute much to the final output, so they are removed. And these weights, the ones which are of higher magnitude, are called winning tickets. Now the pruned network is retrained to completion and then pruned again. And this is repeated until the model is of the required size. This is called iterative pruning. So this technique of iterative pruning can reduce networks to 10 to 20% of their size while retaining performance. But a major limitation of this technique is that training and inference time is not reduced at all, because modern hardware such as CPUs, GPUs, and TPUs do not perform well on sparse matrix operations. This is a flowchart of LTH-based training. We first train the network normally. Then in a loop, we prune the networks which are of lower magnitude and reset the remaining weights to their initial values and retrain. This is continued until you get the required percentage of weights. And after we get that, we continue with the usual flow of testing the model and tuning hyperparameters. To address the limitations of LTH, we look at early bird tickets. So in their research, they show that winning tickets can be identified early without training to completion. EBT uses a metric known as mask distance to identify when to draw tickets. Mask distance is nothing but it keeps track of how many weights change between the previous iteration and the current iteration. And if the distance reduces below a set threshold, we draw the tickets. This method, known as EB training, provides 2 to 4x reduction in computation as well as training time. And additionally, a channel pruning is used instead of removing individual weights. We'll now see what channel pruning is. So here is an illustration of channel pruning. We know that convolutional layers have a number of channels, which are 3 channels for the input layer and gradually increasing. So we associate a scaling factor with each channel, and this scaling factor is a trainable parameter which is trained along with the network. So after training, we remove the channels which have low magnitude of this factor, and then we create a new network consisting only of the remaining channels. This way we get a compact network without removing individual neurons, but by removing entire channels. This is a flowchart for EBT-based training. So after every training epoch, we calculate the mask distance. If it's less than a set threshold, we prune the network by channels and train the model to completion. So notice here that there is no repeated full training of the model as seen in LTH. So the training times are a lot better. We train the model at most 2 times fully. And we also apply 2 GAN specific improvements. The first of them is called top K training, where we only use high quality images to update the generator weights. So basically, the images that the discriminator can identify easily are discarded in top K training. The second one is called 2 time scale update rule, which is simply nothing but using lower learning rate for generator and a higher learning rate for discriminator. And we apply our model on 2 data sets. The first is fashion image consisting of 70,000 28 by 28 pixel grayscale images. The other is a larger data set named deep fashion consisting of 800,000 images of 128 by 128. Here are some sample images from the 2 data sets. On the left side, you can see deep fashion, which has lower variation but higher quality, whereas fashion MNIST has higher variation but of low quality and grayscale images. In brief, our method looks like this. We generate images of fashion articles using GANs and optimize the models using LTH, GBT, channel pruning, along with techniques like top key training, label smoothing, and 2x scale update too. We train our GANs on 2 data sets, fashion image and deep fashion. The optimized GANs are then deployed to a client-side web app. Our network architecture is a standard DCCAN architecture, which has 4 blocks of convolutional. The generator has 4 blocks of convolutional transpose, batch normalization, and ReLU, whereas the discriminator has convolution, batch normalization, and leaky ReLU. Now over to Ritik.
Thank you, Samyak, for the informative information. So coming to the results that we received from the training of the GAN models, as we can see upon LTH training, when we prune the weights for 20%, we get the following result on the top left. When we continue to decrease the threshold of weight pruning, we receive a certain degradation in the quality of images. And we notice that at a cap of 61% to 55%, the image quality starts to decrease gradually. And so this indicates that LTH doesn't provide that great of a method to generate images. Hence, we go for a method of channel pruning and early bird ticket training. So these are the outputs that we received from channel pruning. Upon 50% of pruning the channels, we receive the following on the top left over here. And once we increase the number of channel pruning percentage to 70%, we also notice that the image quality doesn't reduce drastically and it's still quite considerable. Upon increasing it to 80%, we can see a few distortions in the image, but the quality of the image still remains considerable. Coming to the results on a color dataset, which is our deep fashion dataset, since every fashion designer would not work with grayscale images and black and white clothing, and they would prefer color. We have deployed 2 deep convolution GANs of size 64 by 64 and 128 by 128, and these are the results that we obtained. Since the deep convolution GAN is a very basic GAN architecture, the results over here are slightly distorted, but they can be improved later on. So our main focus of the paper was to be able to decrease the size of the GAN and to be able to deploy it on a client-side app so that the speed of the GANs and the weights have been reduced. Upon channel pruning, we conclude that our results where we prune the channels, we receive a reduction of around 16%, 16 times reduction in the number of parameters, and a 21 times improvement in the speed of inference time. Along with this, we also say that there's a 4-time improvement totally for the training and the prediction of the images by the GANs. And the training time per epoch also is reduced considerably when we perform the optimization techniques such as lottery ticket hypothesis and early bird ticket trainings. Yeah. So coming to a conclusion, basically, the heavy weighted GANs have been reduced in their weight reduction significantly, and this can be deployed on any mobile phone and laptop, leading to lower inference time and lower training time. So I will be showing you a demo right now after this. So coming to the future improvements which can be done on our work, we could also use a standard metric quality to detect the image quality produced by our GANs, instead of just having a visually plausible and viable option. We can also apply evaluation metrics. To improve the quality of the GAN, we can use state-of-the-art GAN such as style GAN, fast GAN, and others. Since channel pruning usually involves batch normalization, we could also find a different way where we extend our layers and not use batch normalization, which could also lead into providing higher resolution of images. And since the data set was limited to around only 70,000 images from the fashion MNIST, we could also get a higher data set from various fashion designers if they allow us. So You can, each of you, if you want, you can go to the certain URL and try out the client-side demo for yourself, but I'll be showing it to you right now. So as you can see, this is the website where we have designed. These are the trained DC GAN models, and originally the model size after training was around 50 MB. But after applying LTH pruning and channel-based pruning, we have reduced the size down to around 5 MB so that it can be deployed on any kind of web app or any kind of mobile app in the near future. So let's say a fashion designer provides an image of a shirt like this, and we provide him a method where we can interpolate between the random vectors and change the shirt and provide him various designs. Let me just stop sharing my video so it doesn't lag. So as you can see, you can convert a shoe from you can convert it from a shoe to a shirt from basically interpolating between the random noise vectors, even though you've just given it a shirt. So it basically extracts the features out of this shirt, and from a given shirt, you can receive a shoe. Coming down to the same for using the deep fashion data set, we also see that the size of the initial model after training was around 50 MB, but on applying of early bird ticket training and LTH, we have brought down the size to around 13.9 MB. So once we interpolate between the random vectors, we see that you can change the variations in the colors, and we can also add different styles later on by using conditional GANs. Yeah, so if you want me to generate another different image, you can go ahead and generate different images, and you can just reset the random vectors and play around with it. Later on, this will be improved, and we'll be providing the fashion designer with options to providing labels and also his own customizations. The main idea was to be able to deploy it on the web app, which we have achieved. Coming back to the presentation. Thank you for your time. This was our presentation. Ritik Hariani and Samyak Sarnayak signing off. Thank you.
Thank you.
Start talking.
Thank you to our presenters. We will now open the floor to questions from the audience. So if you have any questions, please type them into the Zoom chat or on Hoova, and the presenters will address them.
So we have a question here from Macmillan. So he says, what would be some real world applications apart from fashion synthesis? So as we all know, today's technology involves of using many deep fakes, and many other apps are coming up where there are various applications for generative adversarial networks in AI. So providing a suitable way of reducing the weightage of a network so that the app size can be reduced based upon the other backend and the front end, which every app would usually consist of. So our main idea is to reduce the weightage of the architectural, neural network models so that the overall size of the app is condensed, and this would also lead to like reduction in the size while retaining the amount of image quality and video quality if we plan to extend it to videos. It's basically a generalized approach of reducing the weightage of every GAN network, and it's not uh, relevant only for fashion synthesis. We can apply it for any other network which uses GANs.
Thank you for your answer. I have another question. If not GANs, what other technology do you think you could implement to serve the same purpose of fashion synthesis?
Samyak, would you like to take up that question?
Yeah, sure. Other than GANs, we could look at technologies like variational autoencoders or other generative networks. So I am familiar with autoencoders and variational autoencoders. And these don't use two networks playing with each other. Instead, they use one network which where you pass in the input and it learns to generate the same input using an encoder-decoder model. That's one alternative. And a technique could be applied to autoencoders as well, but we have not tried that.
Okay, thank you for your answer. We will wait another 2 minutes or so for some more audience questions. So if anyone wants to ask a question to the presenters, please type them into the Zoom chat. Okay, we have another question. Since you used the lowest parameters, does that have any effect on the results? It makes the speed faster, but does it have any impact on the results?
Could you please elaborate on what you mean by lower parameters?
I believe it's referring to the different speed, the different p-values that you used. There are you use certain parameters that correspond to a certain inference time and a certain speed up and sparsity. Does that question make any sense to you?
Samyak, do you want to take up the question? Yeah.
So I think the question is that because we are taking just a few parameters out of all the parameters of the model, does that affect the image quality in any way? So as we showed in the results, you could see that as you remove more and more of the parameters, the image quality keeps decreasing. but up to like say 70% or 60% in LKH and 80% in EV training, you can see that the image quality doesn't decrease that much. And so up to a point, you can remove parameters without changing the output image quality as much. And that's what the lottery ticket hypothesis says, that not all of the neurons in the model will contribute to the final output. Some of them will be closer to zero and they don't contribute much. So removing them doesn't affect the output quality that much. So we identify these neurons and remove only those. That way we get a smaller model while also retaining most of the performance. Currently, we do not have any metrics for it, as we said in the future work section, that we'll need some kind of metric to figure out how much the model degraded as we remove the neurons. Does that answer the question?
Yeah, thank you. If there are no more questions from the audience, we've come to the end of our session. So our next event is another student presentation that will start in a few minutes. So I would like to thank our presenters as well as the audience for attending. So to attend the next event, please head to Hoover to find the appropriate Zoom room. And thank you very much. Thank you to the presenters again.
Thank you, everyone.